I have the opportunity to live in Las Vegas, Nevada, and one of the sayings I've heard about Las Vegas is that what happens in Vegas stays in Vegas. Or now, what happens in Vegas goes on social media. In the world of VLANs and layer 2 broadcast domains, whatever happens in a broadcast domain stays in that broadcast domain. But what if a computer like computer 1 sitting here needs to communicate with a computer over at the branch office out here? How is that done? How do we get the traffic out of our local network and send it across the network to the remote location? And the answer is we're going to leverage some additional addressing in the TCP/IP protocol stack, and that is addressing at layer 3, referred to as IP addressing. And when we use that IP addressing, we have devices on the network that forward packets based on that layer 3 IP addressing. Those devices are referred to as routers. So here we have router 1, and that's a router's primary purpose in life, is to look at packets and look at the layer 3 information. And if those packets need to be forwarded, those routers, to the best of their ability, will go ahead and forward that packet to the next device in the path. So if computer 1 was trying to reach a PC at the branch office, the data would need to go here from the computer to the local router, and then from the local router in this topology to the firewall, and then from the firewall to this router, and then from this router, however it routes out to the remote site. And that process of forwarding packets based on that layer 3 information is referred to as IP routing. And although we have separate nuggets on the nitty-gritty details of IP addressing, the basic concept of IP addressing is very similar to streets in a city. For example, it's very likely that the place that you live, whether it's a condo or a house or apartment, is connected to or on a street and has an address. And all of the other buildings and houses on that same street have something in common, and that's that common street name. Well, in the world of IP networks, each of our networks is also going to have a name, very similar to a street name, except we call it a network address. So for our discussion, let's imagine that this is one network here at the corporate office, and that we've assigned a street name or an IP network address. And let's imagine that the first 3 numbers of this IPv4 address represents the network. So all the devices here on this network are going to have an IP address that starts with 10.1.0. That's like the street name. And then they'll have individual host numbers or host addresses. So the printer's at .13, computer 1's at .11. So each of their addresses on this local network would appear as 10.1.0 dot followed by that last number. Another network that we have in this topology is this DMZ network up here, and it is network 10.2.0 for our discussion. So just imagine the first 3 numbers represent the actual network address. And over here at the branch office, we've assigned it the network address of 10.5.0. We've got some PCs and other devices at that location. For example, one of our PCs ends in .55. There's a router connected to that network. It ends in .2. So here's the play-by-play. If the user right here at computer 1 wanted to do a ping request just to verify that it had connectivity over to the device at the branch office that was at 10.5.0.55, the user would get out their command prompt and they would type in ping space 10.5.0.55 and press enter and just hope for the best. But behind the scenes is where it really gets interesting. The local computer says this: okay, I'm going to go ahead and put together a ping request that's destined to the layer 3 IP address of 10.5.0.55. And it's going to be from me. My source address, my IP address, is 10.1.0.11. And that goes in the layer 3 header. In fact, as a point of convenience, it might look just like this. The source address 10.1.0.11 with the destination address being 10.5.0.55. But the computer also says this: uh-oh, I'm on 10.1.0, says PC1, and the destination is on a different street, a different network at 10.5.0. And so at that point, computer 1, behind the scenes, realizes that it needs some help. And if computer 1 has been configured to use a default gateway, and in this topology, a really good default gateway, the person to go to, like the Obi-Wan Kenobi device. Help us, Obi-Wan. You're our only hope to get out of this network. In this case, a good default gateway that computer 1 should be configured to use is the router with the IP address of 10.1.0.1 right here. And if computer 1 has been configured to use that, what computer 1 will do, it will, when it creates the layer 2 frame, it will put its own layer 2 address as the source MAC address, the source hardware address, the source layer 2 address, and it will put the router's layer 2 address as the destination at layer 2. So here, if we go back to this frame that's been captured, the source is PC1's source address, which is this bad boy right here in black, and it's putting the destination layer 2 address of the router interface right here in the layer 2 frame, which is this guy right there. And then computer 1 spits that out on the network. The switches forward that information based on the layer 2 address. That frame arrives at the router, who opens it up, takes a look at the layer 3 information, and says, this packet needs to be delivered to the 10.5.0 network. So if it knows where to forward it, it would then make a forwarding decision of that packet, and at layer 2, it would send to the layer 2 address of the next hop in the path. In this case, it would be the firewall. And then the firewall would get it. It would also look at the layer 3 destination address, and if it knows how to forward it, it would rewrite the layer 2 header and send it to the next router in the path, and that would repeat until it gets to its destination network. And that, my friends, is an overview of how IP addresses at layer 3 can be used by routers to make forwarding decisions across the network. Won't you please, won't you be my router? You know, a router is really only as good as its, first of all, knowledge of how to forward a packet and know where networks are, and secondly, its ability to do so. So for this discussion, I'd like to use this topology right here. This represents, right here, for example, a VLAN, a network. And associated with that network, we've got a network address, and let's use 10.1.0. And we'll use, in this example, the first 3 numbers in the IP address to represent the network numbers. So down here we have the 10.2.0 network. Between routers 1 and 2, we have the 10.3.0 network. Up here we have the 10.4.0 network, and down here the 10.5.0 network. Also, I've assigned IP addresses to each of the interfaces on the routers, and each of the interfaces on router 1 ends in .1, just to make it really easy from a learning perspective to remember who owns those addresses. And then on router 2, each of its interfaces has a last number in its IP address of .2. So as an example, on this network right here, the 10.1.0 network, the router's interface has an IP address of 10.1.0.1, and this PC is at 10.1.0.11. So let's talk about training a router 1 and router 2, on how they can reach a given network. And there's 3 basic ways of training a router on how to reach a specific network. The first of those is simply to configure an IP address on an interface of a router. Because once we configure an IP address on an interface, the router says, hey, I know how to get to this network. It's directly connected. Just like this interface right here, 1/0 on this router. If we configure that interface with the IP address of 10.1.0.1, it knows, bada boom, I'm directly connected. I know how to reach the 10.1.0 network. It's off of this interface. So that's option number 1. The problem, however, is that the router is not going to learn about remote networks, for example, the 10.4 network, because router 1 is not directly connected to it. So for networks that are not directly connected to the router, option 2 would be to configure a static route. A static route is simply giving an instruction. Like if somebody came over to your house and said, hey, how do I get to the nearest convenience store? You could probably tell them based on where you live. Think about it. You go down the street, make a left, and you give them the directions. Well, the same holds true if we're telling R1 and configuring R1 to tell it how to reach the 10.4.0 network, as an example, or the 10.5.0 network. And so what we could do is we could go into the configuration of R1 and say, Dear Mr. R1, if you ever need to forward a packet to the network 10.5.0, here's what we want you to do. We want you to forward the packet out this interface and send it over here to your good buddy R2, and that's your job. And then because R2 is directly connected to that network, R2 already knows how to get to that 10.5 network. So that's our 2 options to begin with. Configure a router interface to be directly connected to a network by giving that interface an IP address, and for remote networks that aren't directly connected, we can configure a static route, specific instructions on how to forward a packet in the direction of that remote network. Now, the big bummer in most networks is that there are lots and lots of routes, and having to do static routes for every single network is a pain in the bazooski. So instead of configuring static routes, the more popular and practical option is to configure and use a dynamic routing protocol. This is where the routers talk to each other. Now, they're not trying to take over the world by talking to each other, but what they will do is they will share with each other information about what they know regarding how to reach a network. So if we configured a dynamic routing protocol between R1 and R2, here are some things that they might say. R1 might say, hey, I can reach the 10.1.0 network and the 10.2.0 network. And R1 says to R2, if you ever need to reach either of those networks, go ahead and send those packets to me because I can reach them. And conversely, R2 may say to R1, hey, thanks a lot. Hey, you know what, Mr. R1? I know how to reach, says R2, the 10.4.0 and the 10.5.0 networks. So if you ever need to reach those networks, you can forward those packets to me, and I'll forward them to those final destinations. And that's an example of a dynamic routing protocol configured on both routers so that they can share routing information and reachability information with each other. And the cool thing about it being dynamic, if we lose a network or we change the topology, the dynamic routing protocols can dynamically update each other so we don't have to manually go back in and statically configure different routes based on our topologies changing. The method of using a static route implies that the administrator, or hopefully the administrator, is configuring specific instructions on a router to tell it how to reach or how to forward a packet regarding a remote network. And we're going to leverage this topology once again in our discussion of 3 different categories of static routes. And the 3 categories of static routes would be specific routes to remote networks, or we could have a static route that identifies how to reach a group or a range of networks. Sometimes that's referred to as a summary of network addresses. And then we also have a default route that we can configure, which is kind of like saying to the router, if you're not sure how to forward a packet to some network and you don't have any other more specific information, just go ahead and do this. So let's do examples of all 3. Regarding specific remote networks, if we had a PC right here who was trying to ping the 10.5.0.55 host down here on network 10.5.0, the PC, when it's putting together that ping request, would identify that it's locally on 10.1.0 and that the remote device is on 10.5.0 based on the layer 3 addresses. And as a result, it would take advantage of its default gateway, and at layer 2 would encode the layer 2 address of the default gateway's interface. At which point, this PC is hoping that when the router receives that, it can continue to make that forwarding decision in the direction over here of the 10.5.0 network. So for example 1 here, a specific route for R1 to get to the network might look like, hey, dear Mr. Router, to get to the 10.5.0 network, go ahead and use R2 as the next hop, the next device to forward it to. So on this network here, this is the 10.3.0 network. R1's address is 10.3.0.1, and R2's address is 10.3.0.2. So our static route that we're configuring R1 would say, to get to the 10.5.0 network, go ahead and forward it to 10.3.0.2, which is the IP address right here on R2's 0/0 interface. And if R1 had that information, it can then forward that frame at layer 2 to the MAC address of router 2, who would then receive it, look at the destination, and continue to forward it to its final destination. And that's because R2 is directly connected to the 10.5.0 network and knows how to reach it. So this is an example here of a static route to a specific network of 10.5.0. The second example of a static route might be a range of networks. We could tell R1, hey, dear Mr. R1, to go ahead and reach 10.anything. Go ahead and use 10.3.0.2 as your next hop. So if R1 gets a packet for 10.4, for example, this static route says, hey, 10 anything, I'm going to go ahead and forward that over to R2, and it's now R2's job to continue forwarding that packet. And the third option right here is the default route. And with the default route, we'll put the example right here as number 3. It's basically going to say, Mr. R1, if you have a packet that's going to a network address that you don't know how to reach, go ahead and use this default route. And the next hop is 10.3.0.2 because R2 is the only other router in our topology. And if R2 is also connected to this big puffy cloud called the internet, it also is not likely going to know all the addresses on the internet, but it also has a default route configured that says to R2, if you don't know how to reach a remote network, you go ahead and forward it to your internet service provider's IP address. So these are 3 examples of how static routes can be used for a router to reach remote networks. And I'd like to do a thought experiment with you just for a moment. Let's imagine that we configured all 3 of these on R1. And furthermore, let's imagine that this PC right here has been configured to use R1 as its default gateway. And this PC then does a ping to 10.5.0.55, this device right here. The packet is received at R1. R1 has a static route that says, oh, I need to forward this to the next hop of R2. So he forwards the packet over in this direction. R2 forwards it down to the PC at 10.5.0.55. And on Ethernet, they'll use ARP along the way if they need to learn layer 2 addresses, no problem there. So when this PC replies, it's going to reply back to its default gateway, presuming that it's been configured to use R2 as its default gateway. And then when R2 gets the packet that's supposed to go back to the 10.1.0 network, what's R2 going to do? And the answer is R2 is going to give up at that point because it does not know how to reach the 10.1.0 network. So what we'd also want to do is train R2 on how to reach these other networks over here, the 10.1 and 10.2 networks. And we could do that using the same combination of techniques, a static route to the specific networks, or we could have a static route for the range of networks, or we could tell R2 to use R1 as a default route and forward any packets that it doesn't know the network destinations of over to R1, and now it's his problem. So here's our game plan. Let's go ahead and configure some specific static routes starting on R1. So on R1, let's train R1 that to get to the 10.4.0 network, it should use R2 as its next hop. Let's also configure R1 that if it needs to forward packets to the 10.5.0 network, it should also use R2 as its next hop. R2 needs to also be able to forward packets. So on R2, we could create some specific routes as well on how to reach 10.1.0 and 10.2.0, or we could go ahead and use a static default route, which basically says, dear Mr. R2, if you get a packet for a network and you don't know how to reach that network, go ahead and use your default route. So let's begin by taking a look at the routing tables on these routers before we add any new configs. And to do that on a Cisco router, we can use the command show IP route. And I'm going to send that command to both router 1 and router 2, and then we can go ahead and look at the results. So here on router 1 is directly connected to the 10.1.0 network, and the 10.2.0 network, and the 10.3.0 network. And this /24 immediately following represents that these first three numbers of 10.1.0 represents the actual network. We'll cover more about that detail in separate IPv4 nuggets. So R1 is directly connected to those three networks. Fantastic. Let's take a look at router 2. So here on router 2 is directly connected to the 10.3 network, the 10.4 network, and the 10.5 network. So let's start our configuration back on R1, starting from the left going to the right. And on the Cisco router, we'll go into configuration mode by typing in configure space terminal, or for short, config T. And then we'll add the command IP route 10.4.0.0 space, then 255 repeated 3 times, followed by 0, space, and then 10.3.0.2. Now let's decode what that is. What we're saying to the router is we're adding an IPv4 route to reach the 10.4.0 network, and these first three groupings that say 255.255.255, that's very much like this option here of /24. It means to the router that we're focusing on the first three numbers in this IP address that are representing the network that we are creating the static route for. And this instruction further says that if you need to ever forward a packet to 10.4.0. anything, the next hop you can use is your good buddy R2 at the IP address of 10.3.0.2. So that one static route teaches the router how to reach the 10.4.0 network, but we have one more, so the 10.5.0 that R1 also needs to be able to reach. So we need to go ahead and hit the up arrow key, and we'll go back and we'll change out the 10.4.0 to a 10.5.0 and press enter. And now we've just entered two static routes. So now if we issue the command show IP route, we have two new static routes right here that basically say to get to 10.4.0 or 10.5.0, I'm going to go ahead and use the next hop of 10.3.0.2, which is R2. Next, let's go ahead and configure a static route on R2 so that it knows how to forward packets in the direction of the 10.1 or 10.2 networks if it needs to. So we'll go back to router 2, and here on router 2, we'll go back into configuration mode. And let's do an example of a default route. It goes something like this: IP route 0000. That represents a default route, and we're going to follow it by another set of quad zeros like this. And then we're going to specify the next hop for this default route. And that next hop is going to be Mr. R1 in our topology, which is 10.3.0.1. We'll press enter. We'll end to get out of configuration mode. And let's do a show IP route once again. So here's the logic. If an IP router receives an IP packet, the router looks at the layer 3 information, looks at the destination, and then looks at its routing table. So if R2 received a packet that had the destination IP address of 10.1.0.55, router 2 is looking at its routing table. That's not it. That's not it. That, none of those are it. It's going to use the default route. And because we have that static route there, that's also why we have this message right here: the gateway of last resort. When you don't know what else to do, go ahead and forward the packet to the next hop that owns the IP address of 10.3.0.1, and now it's his problem or her problem. So next, let's go ahead and test this by doing a ping from PC1, who's at 10.1.0.11, and let's ping out to 10.5.0.55, which is a PC down on the 10.5.0 network, and we'll press enter. And because R1 and R2 both know how to route based on the static routes that we added, we have full connectivity between a PC on the 10.1.0 network and a PC on the 10.5.0 network. Once a network has a dozen or so routes, it's no longer reasonable, and it's kind of tedious actually, to do manual configuration of static routes. So we're going to migrate or move to something more flexible, specifically dynamic routing protocols. So in this topology, I've taken the liberty of adding an additional router, router 3, and also some additional networks. So we've got the 10.10, 10.20, 10.3, 10.4, 10.5, also 10.6 between R1 and R3, 10.7.0 between R3 and R2, and the 10.8 network hanging off of R3. And the benefit of using a dynamic routing protocol is we can get these devices talking to each other to dynamically share information regarding what routes are reachable and through whom. And there's two major camps regarding dynamic routing protocols. There's distance vector example. The classic example of that would be the RIP protocol. May it rest in peace. It stands for Routing Information Protocol, and there's a couple of flavors of it. There's version 1 and there's version 2. Most people are using version 2 if they're still using it. And with a distance vector routing protocol, it's routing by rumor. What do you mean, Keith? Routing by rumor? Well, if R1 believes that he can reach the 10.1 network and 10.2 network, he's going to go ahead and tell R2. And R2 says, great, thanks for the information. If I need to reach those networks or forward packets in those directions, I know I can use you as the next hop. And R2 can propagate that information to other routers. So R2 can advertise to R3 the networks of 10.10 and 10.20, even though he doesn't have first-hand knowledge of those networks. He simply heard about them from R1. Another approach with dynamic routing protocols is link state routing protocols. And with link state routing protocols, we still have routers that are directly connected to networks, except those routers advertise the states, the details regarding the networks that they're connected to. In one of the protocols, called OSPF, which is a very good example of a link state routing protocol, OSPF is an acronym for Open Shortest Path First. And with OSPF, the routers are going to send out little LSAs, link state advertisements. And that way, R2 can take a look at the link state advertisements from R1, along with link state advertisements from everybody else, and then every router, based on all the data, can make their own calculations about the best way to get through the network. So we're not relying so much on rumor from a neighbor regarding everything behind that neighbor. And link state routing protocols like OSPF are more tight, more concise, and more accurate. And usually they converge faster. That means if there's a change in the network, the entire network will figure it out much faster than in a distance vector routing protocol. And then we also have some protocols in this group called hybrid. Now Cisco, a long time ago, created a routing protocol called EIGRP. And if you read Cisco's documentation, they're going to tell you it's an advanced distance vector routing protocol because it uses a lot of the features of a distance vector routing protocol, but EIGRP also uses some mechanisms that are similar to how link state operates. So it can be referred to as an advanced distance vector, or if you wanted to call it a hybrid, no one's really going to look twice if you put it in either of those categories. And one of the features of link state that EIGRP does use, they form like an official neighborship using that routing protocol with their neighbors. And that way, if something changes, they can have very quick information about changing the topology and updating the routing table to reflect the correct routing tables through the network. And one other protocol I want to talk about here is BGP, the Border Gateway Protocol. And that's the protocol that we use on the internet today. And one interesting thing about BGP is that BGP neighbors, two BGP speakers that are talking to each other, they don't have to be directly connected or on the same network. So for example, we could have a router over here, let's call it router 4, and up here we could have router 5, and as long as they have reachability, meaning they have connectivity to each other through the network, they could establish a BGP neighborship, which makes it fairly unique compared to distance vector or link state routing protocols. So we could put BGP if we wanted to also in that category called hybrid, because it has some mechanisms that resemble distance vector protocols, and it also has things like neighborships that are similar to how link state protocols operate. And the benefit of using a dynamic routing protocol is that once we have configured the dynamic routing protocol, changes that are made on the network, links coming up or links going down or new networks being added, all that information can be dynamically communicated to the other routers so we don't have to manually configure static routes. It's pretty amazing to see a dynamic routing protocol at work. So here's what we're going to do in this nugget. We're going to demonstrate 3 different dynamic routing protocols on our topology right here. And currently, the only networks that the routers know about are the ones that they're directly connected to. So there's R1 with its directly connected networks. Here's R2, and then here's R3. Fantastic. Let's go ahead and add RIP. What this does, it goes into configuration mode on each router, tells the router we want to run the RIP routing process, and specifically version 2, that we do not want to do any type of automatic summarization. And we want any interfaces that begin with the IP address of 10 anything to be included as part of this RIP routing process. So we'll send that script to all 3 routers. So here on R1, it's learned 4 routes. It learned about the 10.4, 10.5, 10.7, and 10.8 networks. Here on router 2, it's learned about the 10.1, 2, 6, and 8 networks. And on router 3, it's learned about the 10.1, 2, 3, 4, and 5 networks. Fantastic. Next, we're going to send the command to remove the RIP router process and then put in the EIGRP. We're also telling EIGRP to include any interfaces that begin with 10. So we'll send that out to all 3 routers as well. And you'll notice we have some neighbor adjacencies that have come up. Fantastic. And let's take a look at the routing table on all 3 routers as well. And R1 via EIGRP has now learned dynamically these networks. R2 has learned these networks. And R3 has learned these networks. So next, we're going to remove the EIGRP routing process, and in its place, we're going to put in OSPF process ID 1. And this network statement effectively, in Cisco world, says we want to include every interface that the router is running as part of this OSPF routing process. So with that in place, we'll send that to all 3 routers as well. Next, we have some messages regarding the OSPF neighborships being set up. All 3 routers know how to reach the other networks in our topology, this time because they learned it dynamically via the OSPF routing protocol. So here's router 1, here's router 2, and here's router 3. You know what I've discovered over the years is that users occasionally access the internet. In fact, they do it all the time. And also, we might have servers in our DMZs or at our cloud locations that customers on the internet are accessing as well. So as we consider this network topology, there is a huge problem. And that problem is private addresses. Inside of IPv4 addressing, there are certain ranges of addresses that can be used by anybody. So company A can use them, company B can use them, company C can use them, but they're all private, meaning they aren't routed and won't be forwarded over the public internet. And here are some examples of the private address space. Anything that begins with a 10, or anything that begins with 172 dot and then 16 through 31 dot anything, and then any IP address that begins with 192.168 dot anything. Those are all IP addresses at layer 3 that the internet will not forward because they're part of the private address scheme. And that's going to cause some problems in our network if we've got some VLANs, which are layer 2 broadcast domains, and associated with each of those respective VLANs, we're using IP network addresses, which we are, in that private address space. So here we have a layer 2 VLAN 100, and associated with that, all the devices on that VLAN 100 are using the network address space of 10.1.0, those first 3 numbers being the network, and then we have the individual computers with the final number in this topology. So computer 1 would be at 10.1.0.11 inside of VLAN 100, and computer 2, perhaps its last number is 22, and its IP address is 10.2.0.22. And so the big problem is, though, is that when computer 1 or computer 2 wants to forward packets to servers on the internet, we'll draw a little happy server out here because he's up and alive on the internet. Let's imagine his address on the internet is 67.83.0.2. So that's the publicly reachable IP address of this server on the internet, and computer 1 and computer 2 want to send packets back and forth between themselves and that server. And the problem is they're using private IP addresses which the internet will not route. So to solve that, we're going to go ahead and do a little game called lying. We're going to lie. We're going to lie about the real IP addresses that these devices are using. And that lying game regarding lying about the IP addresses is called network address translation, or its cousin, port address translation. Both of them have the end result of taking a packet that's going from a private IP address going out to the internet, lying about that IP address to make it appear as a globally routable address, an address that can really work on the internet. It's always good to start off with a plan as far as accomplishing network address translation, and to do so, let's go ahead and use this router right here, and that will be our NAT device, our NAT router. Let's also imagine that working with our ISP, we've been assigned the routable internet address of 23.1.1.1. So that's a starting point, having a routable address that we can use on the internet. And if we only have one IP address, we might have hundreds or thousands of customers that need to be translated into that one address. That is what's referred to as port address translation. And let's talk for a moment why it might be called port address translation. If we have 1,000 computers and they're all sending packets out to the internet and they all appear like they're coming from one single IP address, when those replies all come back, it would be handy if the router could keep track of all those individual sessions so it could untranslate the replies and send them back to the actual computers. So to do so, the router, as it tracks all those sessions going through it for translation, is going to be looking not only at layer 3 information, but also layer 4 information, including port numbers. And by using a combination of both layer 3 information, for example, computer 1's source IP address, as well as the ports involved at layer 4, if we're using TCP or UDP, all that information goes into the translation table so that when the reply comes back, the router can keep track of which PC should receive that reply that's coming back from the server. And because it's doing port address translation, a client, when it makes a request, may use port 1234, and the router could go ahead and use something completely different, like 4359. And as that request goes out using a source port of 4359, the server is going to reply back to that port, at which point this router is going to untranslate that and put back 1234 and send that packet back to that port. So in that sense, it literally is. For UDP and TCP traffic, it is also doing port address translation as well as the IP address translation. So we can use the technique of port address translation to translate lots and lots of hosts on the inside to a single IP address on the outside. In a separate, we focused on port address translation, and in this, I'd like to pick up on the same topology and discuss network address translation with a one-to-one mapping between a host on the inside or DMZ of our network and the global routable internet. So we can use the technique of port address translation to translate lots and lots of hosts on the inside to a single IP address on the outside. But what if we have a server, like one of these guys right here, that a user on the internet, like Bob, needs to access? To facilitate that, it's very likely we're going to have a static, hard-coded network address translation. And that implies a one-to-one relationship. So if we have a server on the inside that has an internal address on this DMZ of 10.7.0.77, that's its real IP address, what we could do is we could hard-code that to a routable address on the internet. So if our internet service provider gave us 23.1.1.50, we could statically configure a translation on this router, this NAT router, between this inside address and this globally reachable address. And that way, Bob on the internet, if he makes a request to this global address, the router says, oh, I know exactly where that goes. The router translates that address over to 10.7.0.77 and forwards the packet to that server. So NAT is usually a one-to-one correlation between one inside address and one outside address, where port address translation is usually a many-to-one scenario. In the case of hundreds or thousands of computers, all being overloaded to a single global routable address, and the router using additional layer 4 information and ports to keep track of all those translations. So another question might come up, well, what would this translation table look like on a router doing network address translation or port address translation? And here's an example of just that. This is from a Cisco router. In this column, the pro doesn't mean it's not an amateur, it means protocol. So these are the various protocols that currently have translations in place. The one here at the bottom implies a static translation for NAT that simply maps the internal resource of 10.7.0.77 to the global routable address of 23.1.1.50. The inside local implies what the clients are really using. So based on this translation, a client on the inside at 10.1.0.11, very likely PC1, used a source port of 23,904, and then when the router translated that and forwarded the packet out to the outside, it used the IP address of 23.1.1.1, and it chose to use the port 4501. So from the internet's perspective, it looks like it's a client coming from the source IP address of 23.1.1.1 with a source port of 4501. Although the reality on the inside is this. So when a reply comes back from that server on the internet, the router would then untranslate that, both the layer 4 and the layer 3 information, so that when the client received that response, it's what the client is expecting to receive back from the server. We also have an entry from a client at 10.2.0.22. That could very well be computer 2 with a source port of 51,553, which got translated out to the global address of 23.1.1.1, appearing to the internet to use a source port of 4097. And because the layer 3 information from both of these hosts are being mapped to the same exact global address, the same routable address of 23.1.1.1, this is an example of using PAT, port address translation. And if we take a look at the static translation being used between 10.7.0.77 and 23.1.1.50, that bottom entry would be an example of NAT as far as a configuration on the router with a one-to-one relationship between the inside real address and the mapped address. And then we can also see with this line right here that that translation currently is in use on this router. The router didn't need to translate anything at layer 4. So the TCP source port that the client chose to use is still being used as that packet is forwarded out to the outside with its new source address of 23.1.1.50. I remember hearing this saying that the packets don't lie. So let's leverage that reality and take a look at some packets both before and after they go through a router that's performing network address translation. And so let's use this topology once again. And for the internal device, let's go ahead and use PC1 or computer 1 that's at the IP address of 10.1.0.11. Let's also imagine that there's a server here on the internet, and its IP address on the internet is 67.83.0.2. Oh, wait a sec. Oh my gosh, hey! So I just got a text that my grandson was just born. His name is Connor, 6 pounds, 13 ounces. All right, so I'll reply to that text after this nugget is done. So that new baby is from my son Brody, and more importantly, from his wife Sabrina. So congratulations to you both. I'll get right back with you. So getting back to our topology with the network address translation, and network address translation doesn't have to be done by a router. It could be done by a firewall or a router. And in some environments, it's possible that we're having network address translation or port address translation in multiple points in the network between the client and the server that it's communicating with. So for our protocol analysis, let's imagine that this computer at 10.1.0.11 is making a TCP synchronization request over to the server, and that it's using the source port of 21,585. So its source IP address will be 10.1.0.11, and the TCP source port will be 21,585. Now, if we're using PAT, the device performing the network address translation with PAT gets to choose what the new source port is going to be. So for discussion, let's imagine that the translation device is going to use a new source port for the translation of TCP port 4096. And regarding the IP address for translation, let's use the IPv4 address of 23.1.1.1. So before translation, we have the source IP address and source TCP port. And after translation, we'd have the source IP address of this and the source TCP port of this. And if this client is sending a packet to the destination right here of the server, that destination is not going to change in the packet after the translation. The destination is still going to be 67.83.0.2. And let's imagine that server is listening on TCP port 21,586. Some custom application that's using that port. As that packet goes out, all the NAT/PAT device is going to be doing is swapping out the source information, and it's going to leave the destination IP address and the destination port intact. It's not going to change those. And then when the server responds back to the IP address and port, the translation device will then untranslate the port and the IP address, and then forward that response from the server back to the client at the IP address and port that client is expecting that response to come in on. So here we have a capture of the original packet somewhere on the network before it went through the translation device. So here we have the source IP address of 10.1.0.11, the destination address of the server, and then here we have the TCP source port and the TCP destination port. And then after translation, we can see that the source address is now 23.1.1.1, and the source port has also been translated to show a source port of 4096. We can also see right here in the packet capture that the destination IP address and destination port after translation is the same as it was before translation. Because all we're doing on the initial packets to go out to the servers is we're simply translating the source IP address and source port. And if we were to look at the translation table on the router or firewall that's doing the translation for us, it would reflect that same information. So inside local, the real IP address that the PC is using is 10.1.0.11 with a source port of 21,585. That matches up with our protocol capture right here. It's also showing us that when it gets mapped, it's going to have an outside routable address of 23.1.1.1, which maps up with that guy right there, and also a new source port of 4096, which is reflected right here as well. And regarding the server information, the destination port and the destination IP address did not get changed based on the translation we're doing on behalf of the client who's going out to the internet. In this nugget, we've used Wireshark to take a look at the before and after picture with port address translation. When dealing with other people, we like to be treated fairly. Well, in computer networks, we don't always want to be fair to our traffic. So in this nugget, I'd like to chat with you about a mechanism we can use to identify traffic for special treatment, and that is in the form of an access control list, or ACL. And access control lists are usually used as part of a 1-2 punch. The first part of the 1-2 punch is to identify specific types of traffic, either looking at information at layer 2 in the layer 2 header, or looking at information in layer 3 header, and sometimes even in layer 4 at the transport layer. And then based on that, give it special treatment, or give those packets or segments or frames special treatment as they go through the network. And a logical question might be, well, if I'm a packet and I want special treatment, what could that special treatment look like? Well, one element would be whether we're going to permit or deny that traffic on the network. Maybe we don't want some specific type of traffic. Let's say we have it out for the computer one here. So computer one is at address 10.1.0.11, and we see that that computer has been going out to the internet to a specific server at 67.83.0.2. And as it communicates with that host, it's using it the transport layer, UDP, User Datagram Protocol. And if we did not want to allow that, we could first of all create an access control list that identifies that traffic between these two specific IP addresses and at layer 4, including the fact that it's UDP. And we could simply say we want to deny that traffic and then apply that access list to the router interface. Another example of where an access control list can be used is to identify traffic that should be translated. From an earlier nugget, we took a look at network address and port address translation, where we translated the source IP address of computer 1 before it went out to the internet. Well, we can be very granular with exactly who gets to be translated, and we can do that also by creating an access control list that identifies the source IP addresses that we're willing to translate, and then combining that with the translation rules on our NAT device or PAT device. Only those devices that match that access control list will actually get the benefit of the translation as they go through that NAT router. Another variation of that is maybe we have two servers. One's a web server on port 80, and one's a web server with security on TCP port 443. However, if we only have one IP address that's globally reachable, let's say we have 23.1.1.50 as our only reachable IP address from the internet, we could set up an access control list that says specifically if the traffic is coming in to that IP address on port 80, then we're going to translate to this server right here. We'll call it server B. And if the incoming request is destined for TCP 443, based on the access control list and the translation statement, then we'll go ahead and forward that traffic over to server A, who's listening for those incoming requests on port 443. And when we're doing translation on a specific port like that, that's commonly referred to as port forwarding, because we're basing the forwarding decision specifically on the port that's being requested. Another great example of where we could use an access control list is to identify traffic that we want to give preferential or different treatment to as that traffic crosses our various network devices. An example could be traffic that's crossing this wide area network link that's connecting our corporate headquarters over here on the left to this branch office over here on the right. And wide area network connectivity is going to be relatively slower than our high-speed Ethernet connectivity up here, generally speaking. And if it is, we may have traffic that needs to be sent back and forth over this link, and there may not be enough bandwidth to send all that traffic the moment it shows up at the router. And the concept of traffic shaping is to help the routers not just drop all the traffic, but rather to queue it up and make sure that the data can be sent, even if there's temporary bursts where we have more traffic than we can send instantaneously. Another performance-related concept that can be used in conjunction with access control list is QoS, which is an acronym that stands for Quality of Service. And as packets go into the network, depending on what device they come from and what device they're going into, we can do special manipulation, or they call it marking, of the packets in the IP header, and then we can train our routers to pay attention to those markings. So if we have a user like Bob, actually a better example, if we had an application like voice over IP, which is very sensitive to delays, if we want to have a conversation and it's going over a voice over IP network, we can't tolerate large amounts of variations or delays. So with quality of service, we could mark all that voice over IP traffic with specific markings in the IP header, and then we could train the routers that when they see that traffic, they should give that traffic priority treatment with the intent of making sure that our voice over IP communications are working, or at least working well enough so that the users have functionality. And when we're doing quality of service, when we're marking packets and treating various packets differently at routers, that can be referred to as differentiated services. We're differentiating between one protocol or one set of markings and another. Differentiated services is what that's implying. We can also do marking of traffic and prioritization of traffic at layer 2 in switching, and when that's done, that's often referred to as paying attention or working with COS, which is class of service. So if we see someone referring to class of service, we can think to ourselves, okay, that's dealing with the preferential treatment based on layer 2 frame markings. And if we hear the concept of diffserv or QoS, quality of service, that's going to be higher up in the protocol stack, primarily focused on markings in the IP header at layer 3. Seeing a demonstration often helps reinforce a concept. And that also applies to this nugget. Let's go ahead and do a demonstration of setting up an access control list to filter specific types of traffic through our network. So we'll use this topology, and here's our objective. We want to filter all UDP traffic. So at the transport layer, we want to filter all UDP traffic between computer 1, which is this guy right here at the IP address of 10.1.0.11, and the server out here at 67.83.0.2. And before we apply any filtering, let's just verify basic connectivity with a few protocols between this PC, which is at 10.1.0.11, and the server. And this little virtual machine that I'm running as a virtual PC has a command called trace, which, among other things, is going to help us verify connectivity all the way to the destination, along with the path that we're taking to get there. So we're going to use the command trace, the IP address of our server, which is 67.83.0.2, and then I'm doing a -P space 1. Now, protocol number 1 is ICMP, which means it's going to do this trace leveraging ICMP. If we change that number for the protocol to a 6, 6 is TCP. And that'll come in handy in our testing as well. And then if we change it to a 17, 17 is the protocol number for UDP. And see, the cool thing is, if we set up an access control list that just blocks one of these, we can still verify connectivity with the other two. So let's get a baseline by testing all three of these first. So the first one is a trace with ICMP, and then we'll put 6, we'll do our trace with TCP, and then last but not least, we'll put in a 17 there for the protocol number, and that'll use UDP. All right, so with our baseline set, let's go over to router 1. So here on router 1, let's take a quick look and see if we have any access control list already in place. And we do have one access list in place. It basically is identifying any source PCs that have the IP address of 10.1 or 10.2. So this access control list, access list 1, is being used with translation statements for the benefit of network address or port address translation, depending on how the rest of the router is configured. So let's go ahead and create a new access control list that we can then apply to the router interface to block the UDP traffic. So we'll do that by going into configuration mode on the router, and we'll create the new access list with this entry. And let's break it down. This is creating an access list numbered 100. The action is deny regarding this access list entry, and what we're looking for is anything at the transport layer, which is UDP, and if it's coming from the host 10.1.0.11, that's the source, going to the destination host of 67.83.0.2, which is our server. And if we knew specific UDP port numbers, we could also tack them on with a little EQ space and then put the actual port number there. But in our case, what we're going to do is we're just going to block any UDP traffic between computer 1's address and the server with an access control list that we're going to use for filtering of traffic. If we applied this access control list to the interface gig 1/0 on the router, it's basically going to follow this to the letter. It's going to compare all traffic coming into the interface, and traffic that does match is going to be dropped. But traffic that does not match by default is also going to be dropped. So we need one more entry to permit everything else that's not exactly matching the first line. So this second entry in our access control list numbered 100 says it wants to go ahead and permit traffic if it happens to be IP, which is referring to layer 3. That means anything that's IP from any source to any destination. So we'll go ahead and press enter, and let's take a look at this access control list. So this access list, list 100, has two entries, has line number 10, line number 20, and after this is applied to an interface, these entries will be processed top to bottom. So every packet coming into the interface is going to be checked against line number 10. If it doesn't match, it'll be checked against line number 20. And then our last step is to apply this to an interface. So we'll go to interface configuration on router 1 for gig 1/0, and we'll use the Cisco command of IP access group 100, and then we want to apply this to all inbound traffic on that interface, and we'll press enter. So our next step is to test it. So let's go over to PC1 and do a test. And we'll do a trace with ICMP. That should work. Great. We'll do a trace with TCP. That should also work. However, if we do a trace with protocol 17, which is UDP, that should fail. And right here we have some telltale signs that that's happening. Communication administratively prohibited, which is the router communicating back to PC1 saying, sorry buddy, couldn't do it. One interesting note about enterprise and corporate networks is that they generally have more features and bells and whistles and security than a small office home office. So from a physical equipment perspective, one of the big differences is going to be in the switching environment. So in a small office home office, we may have a simple 8-port switch. However, in a corporate environment, they're probably going to have racks and racks of switches, and they're also going to have different ones based on where they are. They'll have some in the wiring closets, referred to as access switches. And those access switches can then connect down to bigger switches at or near the data center. Those are often referred to as distribution switches. That's also a likely location to get connectivity between the corporation and other sites, which could include connectivity out to the internet or connectivity up to a remote office or branch office. And in the main distribution area near the data center, there's going to be a lot of traffic that flows through that point in the network. And to help facilitate moving all that data, the higher end switches use a feature known as distributed switching. And if we have a layer 2 frame that needs to be switched, when the frame comes in, if the switch has to take a moment and think about that, okay, that frame came in here and it needs to go out this port. If that decision has to go to a centralized brain every single time a frame comes in, that could be a bottleneck if we have hundreds or thousands of ports. And that's where distributed switching can help. With distributed switching, the forwarding information is distributed out closer to the ports, or at least the module on that larger switch where those ports exist. And then as a result, when a frame comes in on this port that needs to be sent out that port, because that learning and forwarding logic is distributed down at this level, this module doesn't have to check in with the centralized brain to ask it, okay, what do I do? That information about forwarding is cached and distributed, so the switch can make that forwarding decision without having to bother the central unit every single time. Also, what we'll typically find in corporate environments is that they'll have some switches that also incorporate routing functionality in one box. So the question might come up, well, what do you call a box with a whole bunch of ports that can do layer 2 forwarding based on layer 2 information in the frames, as well as make layer 3 routing decisions? Is it a layer 2 switch or is it a layer 3 router? And the answer is, it's kind of both if it has both those functionalities. And I've seen this often referred to by many different vendors as a multi-layer switch. So if you see the term or hear the concept multi-layer switch, it could be referring to either layer 3 routing of IP packets or forwarding of layer 2 frames, all built into the same box, referred to as a multi-layer switch. Back in the 80s, when I had my first official corporate job in the world of IT and networking, we had dedicated leased lines between our location, which was in Southern California, and a branch office or remote site in Northern California. And the leased line was fairly expensive. It was a dedicated circuit between us and our other site. And because it was really expensive, we had some fairly intelligent gear on both ends that could do things like time division multiplexing and other kind of tricks. And that way we could utilize that dedicated circuit as much as possible between our two locations. And a dedicated circuit, a dedicated leased line, is an example of circuit switching, where we're moving data frames between point A and point B over a single path every time. So all the traffic would go over that leased line from point A to point B and then back from point B to point A. Now, we love the fact that we had connectivity, but we didn't love the cost. So in the late 80s and early 90s, the big rage was a new technology called frame relay. And effectively what it did was this. We had a service provider, I'll put SP for short, and instead of having a dedicated leased line, we would go ahead and rent a logical circuit. So the central site would connect to the cloud, the remote site would connect to the cloud, and then inside the service provider cloud, we'd have a logical connection between the two. But it wasn't a physical dedicated circuit. And in this cloud, the service provider had a lot of different paths. So we might have some of our packets go over one path and other packets go over a different path. The key is it's all packetized. So we're not using the same exact path as that traffic is moved or forwarded or switched, if you will, over that service provider network. And that concept of individual packets going over a network and perhaps not all of them taking the exact same path is referred to as packet switching. And from a customer perspective, we really don't care if all the packets take the same path as long as they get to the other side in a timely fashion and in the right order would be helpful as well. Another useful idea, and it's up and coming and will be for a long time to come, is the concept of software-defined networking, or SDN for short. Because think about a large network with lots of gear. If we had to administer each one of these by connecting to them and then configuring them, whether they're switches or routers or firewalls or access points, connecting to each one of those is a pain in the bazooskies. So with software-defined networking, the concept is this. We're not going to have the humans touch the actual infrastructure. Instead, we're going to have humans interact with applications. And that application could go both ways. It could give us information as a human, and we could also make changes. But we're doing it through the application. And those apps are communicating to controllers. So this controller, let's say we have a controller right here on the network that's connected to our network infrastructure. Our applications would interoperate with those controllers, and the controllers would then interoperate with the actual infrastructure. I hope this has been informative for you, and I'd like to thank you for viewing.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.